recording. Okay, so we're recording. All right, let's do this. Change that there. Okay, all right. So I wanted to go ahead and put this on the recording regarding the final. So as you know, I was going to send out a poll that said like who wanted to do the final Tuesday, but who wanted to do the final Wednesday. But I found out there's a little bit of a problem with that. So the reason for moving the final from Tuesday to Wednesday is because there's people that have 3 finals in one day. But then there's a lot of people in here that also have capstone, who have capstone presentations on Wednesday, right? So it's like, wait a minute, if I move it, I might interrupt the capstone presentations. But if I don't move it, we got 3 exams a day. But here's the thing. It looks like, how many people here have 3 exams and are in capstone? That's what I thought. So what we're going to do is I'll just have offerings on both days, right? So if you are in capstone and want to do it Tuesday so that your capstone presentations won't be interrupted, you can take the exam Tuesday. If you have 3 exams a day and you want to do it on Wednesday, you can do it on Wednesday. Simple?
Are you going to stay with Tom on Wednesday?
I was going to suggest the morning, like that's probably like 10 o'clock. Initially, I was going to do that, but then the capstone presentations are in the morning. And that's why I was like, you know. But the other thing is capstone here's what's weird about it. Capstone presentations are dependent upon getting practicing engineers to come and listen. And their availability might change. As somebody who taught capstone, that can change, right? So you might say, oh, we're going to do it at 10, and then, oh, we have to do it in the afternoon, right? So that's why I thought it would be easier. Let's just do it both days, and so as long as you take the exam, you're good, right? Sound good?
What time on Tuesday would be the final?
Yeah, we're in the middle, right?
10:15.
Yeah, so you would have one of your finals in the morning. Is it transportation or geotech? So you'd have your geotech one. So for if you were going to have 3 exams, it would be geotech, steel, transportation. And so if you're going to have 3, you can take a break in the middle and do it on Wednesday. Is that everybody okay with that?
Is the one on Wednesday at 10 still?
Yeah, that unless somebody tells me, like I haven't heard anything that 10 wouldn't work, right? The only people that it didn't work for are the people in capstone, but for them, Tuesday worked, right? So that's why I figured let's just keep it at 10 and go with that. So is that okay? So I figured keep it simple. That is what I'll send an email in effect. I didn't want to do the poll because as I was getting ready to set up the poll, I found out the capstone presentations were going to conflict, and I was like, okay, so we'll have to do something else. So sound good? All right, now I will blanketly admit this says attendance grades updated. They are not. I'm a little behind on that. So this week, the attendance grades aren't posted. But the homework grades seem to be rocking and rolling. 6.1 to 6.2 are graded. 6.3 is being graded. 6.4 is due today, but I'm not giving you a homework this weekend.
Thank you.
Because today is a somewhat heavy lecture. Today, we're going to talk about LTB for real, okay? There's a lot of detail and data in this presentation, so I really want your eyes up here. The whole point of you not having a homework today is I want what we talk about today to sink in, okay? So I really want to make sure that you're following along with what we're talking about. So I want everybody to sort of pay attention to this because I want to digest what we've talked about for the last little bit. So what we know so far about buckling. This is what we know so far. We know that buckling, okay. First off, first thing we know is that a beam's maximum flexural capacity, is MP, okay? No matter what. MP is a beam's maximum flexural capacity, and we also know that is the capacity if LB is 0. So if I were wanting to plot this, I said LB, and here's the capacity, right? So what do I know? All right, so at LB is 0, the capacity is MP. Like, that's what I know, okay? I have a solution for LTB. That's that equation we derived last time. Now let's take a look at this equation and let's try and make some sense out of it. what happens as LB gets bigger? Like if this value, which is on the denominator, if it gets bigger, what happens to the capacity? It goes down. So if I look at this from a graph standpoint, this should kind of, hold on, this should sort of like trend downward, right? It should sort of trend in a downward fashion, right? That as our LB increases, the capacity should go down, okay? Now, remember, this solution has an error with it. It assumes that moment is constant, and we know that's a bunch of hullabaloo. So we have this moment gradient modifier that corrects it, all right? Again, any excuse to use the word hullabaloo is great. Okay, now, if all the m values are constant, CB is 1. That's really easy to look at the equation, right? Because if all the m values are the same, we have 12.5 on top, 2.5, 3, 4, 3, so 3, 4, and 3 is 10, 12.5. 12.5 over 12.5 is 1, right? So if the moment is constant, CB is 1. So this moment gradient modifier is just fine. It doesn't change anything if the moment happens to be constant, right? For any unbraced segment where it's not constant, what have you, a constant or variable, CB is always greater than or equal to 1. And what we're going to do is take this solution and multiply it by our capacity. So CB is going to increase the capacity, but we cannot increase it past MP, okay? Because MP is the maximum. That's the cap. All right, with me so far? Now, I want to take a step back a little bit. I want to talk about this. This is an elastic solution. That is the elastic buckling capacity. And if you go back to column land, would help if I plug this in. If you go back to column land, remember our solution kind of looked like this. So let's see if we can draw some parallels, right? As the slenderness went up, the capacity trended downward, right? Okay, it trended downward. And there were two regions. There was what I'll call zone 1 and zone 2 for columns. There was an inelastic buckling region and an elastic buckling region. Now, a couple of things, all right? How did we determine which zone we were in? Well, we compared the slenderness against this value here, right? Which I'm going to call an anchor point, okay? And so our anchor point was 4.71 times the square root of E over Fy, okay? And depending upon if our slenderness was less than this value, we were in zone 1 or zone 2. When we designed columns, when we dealt with columns, 99% of the time, which zone were we in? Inelastic or elastic? Inelastic. We always dealt with this expression. Very rarely did we deal with this one, right? Okay? Now, let's go back to column land. What were the two reasons that real behavior deviated from ideal behavior? Geometric imperfections and residual stresses. And the reason why I highlight the residual stresses is because residual stresses is what affects this. Elastic buckling is affected more by geometric imperfections because it's elastic. It doesn't have anything to do with the locked-in residual, or it doesn't have anything to do with locked-in residual stresses because we're not talking about yielding there. Okay, does that make sense with me so far? Okay. Just keep that stuff in the back of your head, and now we're going to talk about LTB, okay? Now, if this is the AISC curve for column buckling, I am going to show you the AISC curve for beam buckling, okay? So we're going to talk about 3 zones of capacity and the anchor points that split them, and then we're going to talk about the effect of CB and how CB actually plays into things. So, if we look at the capacity of a W shape, it is split into 3 zones, not 2, okay? So the way that we define that according to AISC is we have 2 buckling zones, like an inelastic buckling zone and an elastic buckling zone. But then we also have our zone at the very beginning, which is just the full plastic moment, okay? So in other words, what we have is we have our graph, right? Here's our graph, right? And instead of a single point that defines whether or not we're in inelastic or elastic, we have 2, right? And so we have this right here is zone 1, this right here is zone 2, zone 3. Okay? And zone 3 is our elastic buckling. Zone 2 is inelastic. Zone 1 is full plastic moment. Okay? And so where these are split up are by what are called these anchor points. So if you remember, let me erase these right here so we can kind of see this. If you remember, we're trying to look at LB plotted against MN. And so we split these up by these anchor points, LP and LR. Okay? So what you do is you basically look at your LB, compare it against LP and LR, and figure out, am I here, or am I here? And for each of those different regions, we have a capacity. Okay? Now, for zone 1, the capacity is a constant. Okay? It's just MP, it's just FYZX. For zone 2, we linearly interpolate between MP and this term MR. Okay? What is MR? MR is the yield moment that has been reduced to account for residual stresses, right? And so we'll see how to compute that here in a little bit. And zone 3 is this. It's just rewritten a little bit, but it's our elastic solution. Okay? Now, we don't want to forget the presence of CB, and so I'll show you how that works here in a little bit. So when you plot that, it looks like this. Okay? So this is really important. This is probably one of the most important slides in CE 414. Okay? This is the AISC LTB curve for W shapes. This will tell you the capacity of a beam against LTB as a function of its unbraced length. Not a function of its span length, but the distance between braces. So, you have unbraced length on the x-axis. We have moment capacity on the y-axis. Does it pass the smell test? What is the smell test? What is the capacity at 0 unbraced length? It's MP. We knew that was going to be the case, right? We knew that was going to be the case, right? Zone 1, constant capacity. Zone 2 is a linear relationship. It's a linear fit between MP and this term MR. And what is MR? It's just the yield moment that's been reduced a little bit. And so we reduce it 30% to account for the presence of residual stresses. So that's what MR is. So if MP is FYZX, MR is FYSX times 0.7. That 0.7 is not a safety factor. If you get asked, no, it's not a safety factor. It's accounting for the residual stresses locked into the shape. Okay? Make sense? Okay, now this is a line. Lines are defined by slopes. We call the slope of that line the beam factor. And so all the beam factor is just change in y over change in x, and so you can compute that pretty easily right here. Zone 3, this is the elastic LTB curve that we previously derived. It's rewritten a little bit, it's written a little differently, but it's the same solution. Okay, I want to stop for a sec to see if this makes sense. With me so far? Now, I think this plot does a really good job of showing you what CB looks like for a given value, but I kind of want to show you what CB does for, or how CB affects the capacity for any value of CB. And so the easiest way to show you that is, I have a little spiffy little guide here. So let me start off by making CB1. Okay. So I have here a plot of the capacity for a given shape. This is a W24/76. It's 50 KSI steel. There's a lot of math in the background to actually do the plot. I'm not going to make you do that. Don't worry. But this is the actual numerical plot for a W24/76, right? So we have a plastic moment capacity of, I think it's something like 750 foot kips. I believe I did factor this because this is phi MN, so I included my phi value. Here's the LP value. Here's the LR value. In fact, you know what would be nice? Why don't you open up table 3-2 in your AISC 15th edition steel construction manual that I know everybody brought with them, and tell me what is LP and LR for a W24/76. Remember I told you there's all those values that, oh, we'll use them. We're using them. Isn't that exciting? The ZX tables.
6.78 for
A W24 by 76.
What do you want?
The LP. 6.78. Here, I'll write that on the board. Okay. So, LP, and then LR. Right? So, what you would do is you would look at your beam, right? So, let's say we have a beam, right? And it's 30 feet long, but it has braces at third points, right? So in this case, LB would be what, 10 feet, right? And so you would look at LB compared to these and say, what zone am I in? I'm in zone 2, right? Make sense? Okay. So, and you can see what's going on here. Here's LP of 6.78 feet. That looks about right. What about LR, 19.5? About right there. That looks about right, doesn't it? With me so far? Now, what you are seeing is the effect of of the curve, but CB is not really doing anything. Okay? What happens if CB does something? I want everybody to watch the graph. Okay, now I'm going to change the CB value, and I'm going to change it to, say, 1.3. What happens is it ups the capacity. But what's going on is it's upping the capacity, it's increasing the capacity, but it's cut off. Because I don't care what CB is, your capacity is always limited to MP. So watch what happens. Let's say make it 1.4. Bam. 1.5. Bam. 2. Bam. See what it's doing? It's making the capacity higher, right? It's actually increasing the capacity. But if I were to just numerically plot the curve, it'd go like all the way up here. We say, I don't care what the curve is. You cut it off at MP. Does that make sense? That's what CB is going to do, right? CB is going to cut off your capacity at MP. Because I don't care what the buckling capacity is, you can't really support more load on the beam if the entire cross-section has yielded. Does that make sense? Okay. All right. Now let's go back to this. Let's talk about this a little bit. So I guess the first question might be, well, how do you compute LP and LR, right? I will tell you, I think one of these expressions is about the nastiest equation that you will see in any one of my lectures. This is the equation for LR. It's crazy. Am I going to make you compute LR?
Yes.
No. Why? Because it's right there. You don't need to compute it. We just looked up LR, right? LP and LR are what we call the anchor points that help us determine which zone that we're in. LR is really nasty. LP is actually pretty easy. What if I told you that it might seem counterintuitive, but it's actually much harder to derive LP than it is LR? LR, while very nasty, is just algebra. All you do is here's how you derive LR. I'll tell you exactly how you derive LR. All you do is you take this equation, set it equal to 0.7 FYSX, and just solve for L. That's all you do. It's nasty, and so you got square roots inside of square roots, but that's it, right? All this 6.76, all that is just taking our material constants and just sort of coming up with some constant values to go for it. I actually have a derivation of this. It's not hard. It's actually, I mean, it's algebra. It's a lot of alphabet soup, but it's not difficult. This is a little bit more difficult. You actually have to go and test beams and run a lot of analyses, and it requires some decision making in terms of where are we going to call the ball as to whether or not buckling's an impact or not. It's actually quite difficult to get that done well. But suffice to say, it doesn't really matter. It doesn't really matter because the guy, or table 3-2 computes it for us. Now, zone 1 is easy. Zone 1 is just FYZX. Just plug and chug. Zone 2, however, is a linear interpolation. Now, if you open the manual, this is what it looks like, right? CB times this quantity less than or equal to MP. So let's think about that. Okay, what's in the brackets is just the raw capacity, right? And so what the spec is saying, okay, what you need to do is multiply by CB, but I don't care what CB does, you're taking the minimum of that in MP. That's what you're doing. So, what the spec also does, makes our life a little easier, is what we go from here to here. This term here, this BF term, is just the slope of that line. We call it a beam factor. And so we can take this equation and simplify it a whole lot with this. For table 3-2, do you see beam factors listed? Look at that. By golly gosh gee, there's some BF values listed. It's almost like the manual's trying to make it easier on us. This is what you spent your money on, because if not, you'd have to compute this for every beam, and it'd be a pain, believe me. So, zone 3 is our LTB, our DiffEQ solution. It looks different. I'm going to tell you why it looks different. The reason that it looks different is that this solution is really derived specifically for doubly symmetric eye shapes, like wide flanges, right? So a W24/76 is doubly symmetric. It's the same size top and bottom flange. That's fine. But for bridge plate girders, for example, you will have different size flanges, okay? And suddenly, the solution that we derived doesn't quite work. But you do a little bit of algebra, a little bit of analysis, what you find is that there is a similar solution that looks a lot like this that's in the bridge spec. So the reason they reformulated the expression a little bit is so that when you are designing a bridge, when you're designing a plate girder that's singly symmetric, and you look at the expressions, they're very, very similar. So it's a lot easier for you to pick up how to do bridge calculations as opposed to building calculations. Now, a couple things to keep in mind. Number one, there really isn't a pretty design aid for this one. You kind of just have to chug your way through it. There are more properties that you are going to need, but you can look these properties up in table 1-1. You do need the torsional constant. You need the section modulus. There's a couple other things that you need. One of them is H0. H0 is the distance from center of flange to center of flange, so it's a lookup. You can find it in table 1-1. And then also RTS. RTS is sort of a radius of gyration for LTB. It's kind of like a torsional R value. Again, it's just a lookup. It's plug and chug. When you're using this expression, be very careful with units, right? Because RTS values tend to be in inches, and it's very common for LB values to be in feet. And so if you take L over R, LB over R, this needs to be in inches. So make sure that you're being cognizant of that. Okay, with me so far? Now, I think it's on the next slide. Okay, now, if we want to compute LTB capacity, we need some base values, but this does a lot of work for us. We have the PMPs, the PMRs, we have VBF, LP, and LR. It's already computed for us. So like I said, by the end of this, we were going to know what every value in this table is. I think now we do, other than like how to compute the shear capacity, but we'll talk about that near the end. Now, let me go back. This, I would argue, is one of the most important slides in this class. This is one of the most useful. So what I've done is and this is definitely one to star, this is what I've done is I've taken all of the equations that I just spilled out at you and put it in a nice little pretty flow chart. So what you do is you look at your LB and your LP and your LR and you compare them, okay? If LB is less than LP, boom, you're in zone 1, that's your capacity. Just phi and P, phi FYZX. If your LB is between LP and LR, you're in zone 2, linear interpolation. And notice how in zone 2 and in zone 3, both of the expressions are the minimum of apolojunk and the plastic moment. The minimum of apolojunk and the plastic moment. Because what the spec is saying is, I don't care what CB does, your capacity is limited to MP. Now in zone 2, the CB value is right here. In zone 3, it's in our stress calculation. Here's the expression for FCR. FCR is just the critical buckling stress. Then we take that times SX to get our moment. One term that's a little maybe deceptive in here is this value C. C is 1. You don't really need to worry about it for W shapes. The idea is that if you're dealing with, say, a channel, we would modify this term a little bit to be able to still use the solution. But yeah, this is, I did a lot of work to try and put it all in a single slide. Hold on, let me see something. Okay, I'm going to stop for a sec. I threw a lot of equations at you. My apologies. So far, so good? Everybody able to take it in? Okay. Let's look at an example. I want to analyze this beam. We're going to determine if the beam shown has adequate moment capacity, has adequate shear capacity, and it has if it meets a live load deflection limit of L/360. And the beam is a W24 by 76. Well, by golly gosh gee, it's almost like I planned this out or something, right? You know, look at me. Now, the beam, the dead load shown includes the beam self-weight. So since the beam is symmetric with respect to loading and geometry, we're only going to need to consider one segment. Let me put this in the notebook, and let's get rocking and rolling. Where's my, I'll just do it this way. Hold on. Let's see if it still works. I take the pen. Just think that's cool. Okay. I'll give everybody a sec to copy this down because this is kind of important. By the way, it's almost like that last homework led into this one. It's a simply supported beam with a uniformly distributed load. I wonder if anybody can tell me what CB is going to be for each of these segments. This one's the 1.3. It was 1.14 for the if the whole, yeah. Again, it's like I planned that out or something. It's crazy, isn't it?
Are you saying you plan the lectures?
No, I don't. It's just serendipity. You're giving me way too much credit.
I bet Alejandro does.
Oh, yeah. I'm just taking credit for his work. All right. Get that out of the way. All right. Okay. So again, I'm not giving you a homework this weekend because I want this to seep in, and we're going to probably do some more examples to sort of flesh all this out. Okay. Now, let's look at the structural analysis component a little bit. Okay. First off, this beam is simply supported, subjected to a uniformly distributed load. Did everybody find table 3-1? Did we talk about that? Was that listed on the homework? We didn't actually talk about it, but I did reference it on the homework, didn't I? Yeah. So if you open up to table 3-1, table 3-1 will list CB values for common cases, right? Common instances of analysis loads. And a simply supported beam subjected to a uniformly distributed load is among the most common, right? So CB for both of these segments is going to be 1.3. 1.3. So far, so good? Now, if we want to be if we want to pull a sneaky, what we could do is look at this little guide, and we could probably use this guide to maybe help predict what the capacity is going to be, okay? But we'll go back to that. We'll see if this guide works. Or maybe I made a mistake with putting the programming together. We'll see. We'll see. Okay. Now, if we look at this beam, right, and we think about the moment diagram, what can we tell about each segment? Okay, each segment is going to have a different LB value, but they're both the same, right? Because this 15 feet is LB. That's LB, right? So take a look at this segment and this segment. They both have the same LB value. They both have the same CB value. Do they both have the same maximum moment? Well, yeah. Where's the maximum moment occur in a beam? Like this, in the center. So I only need to investigate one segment for structural capacity. And to be clear, there might be problems later where we have to actually look at each segment and go, what is the maximum moment on that segment, and what is the maximum capacity that that segment can hold up? And it might be that even though this segment has more moment, this segment controls. But we'll get to that part later. Okay, now let's see what we can see. Let's start off with the structural analysis. So the first thing I'm going to do is I'm going to go ahead and just factor the load, 1.2 W dead plus 1.6 W live. And this is a fine approach because both the dead load and the live load they're both the same. They're both uniformly distributed loads across the entire span. Now, why am I not accounting for the beam self-weight right here? Yes. So I don't need to do that. So what is this? Say it again. Second. So MU is WL squared over 8, which is now notice how I'm using 30 feet because that's actually the length of the beam. What are we getting here? Second. VU what is that? Say it again. Second. Okay. All right. So let's look at the capacity. We were given a W24 by 76. All right. So we're going to go to table 3-2. All right. Table 3-2. Okay, so the first thing I'm going to do is I'm going to look up LP and LR. But by golly gosh gee, I already did that. And I got 6.78 feet, 19.5 feet. And from these, I look at my LB. My LB is 15 feet. What does that tell me? Zone 2. Right? And so what I can do, I can say, hold on, let's go to this. All right. So we're in zone 2, right? So because LB is between LP and LR, and so what we're going to be using for a oh my goodness, my surface. What we're going to be using as a capacity check is this term right here, okay? So we need a couple of things. We need CB, we need PHBF, PMPX, etc. So how's this going to work? So what's CB? Well, that's 1.30. We just looked that up. What about PMPX? What was that? 750. What about this beam factor? What is that? And notice how the units, notice the units. 22.6 what? Kips. Because it's the slope of that line, so you take the moment over feet, so you get kips. And then we need LB and LP. So LB is 15 feet, LP 6.78 feet. Bless you. So first thing I'm going to do is I'm going to compute what's on the top row. Bless you. So that is 1.3 times 750 minus 22.6 times 15 feet minus 6.78 feet. And so what do we get for that? Second, how are we doing on that second? Because everybody brought their Casio FX115 ES Plus or similar scientific calculator, right? Everybody did, right? He got called out. Now, what was all right? Okay, so therefore, and this is how I'm going to do this because I don't want to have to write all this all over again. PMN is the minimum of CB times all that stuff in the brackets or PMPX. And what is that? What is it? What is that? It's the minimum of this or PMP, which is 750, which is 733.5. Right? Okay, does that match this? So CB is 1.3. Let me break out my mouse here. That's going to be so much easier to deal with. So, and I'm going to put this on the notebook. So copy, paste. All right, so what do we got? LB is 15 feet. And so that's the capacity. And if I trace that back, it's about 733.5. It's kind of crazy, isn't it? It's almost like that worked or something. What do you think? So let me show you something, okay? So if I want to summarize, so let me show you something. PMN is 733.5. What was MU? 208.75. What does that mean?
sufficient.
It's fine, right? It has more moment capacity than needed. Now, I'm going to show you something. So this is okay. Now I'm going to show you something on the side. And admittedly, this is a bridge engineering term, but you'll get the idea. I'm going to show you what's called a performance ratio. So I'll put it up here, performance ratio. A performance ratio is just an efficiency calc. So we say 708.75 over 733.5. Somebody tell me what that is. We'll say like, I don't know, 3 decimal places. 0.965. If this was a tension member, what would you say? That's all right. Now let me show you something. Somebody tell me what is this for the W24/76. What is that? 315. And what was this? Is that okay? Yeah, that's way okay, right? Now, what's the performance ratio for shear? It's terrible, right? What does that come out to be?
0.3.
Even? That's horrible. Here's the thing. That's okay. Not every shape is going to meet every limit state perfectly. That doesn't mean we're not going to use it. This is still a perfectly good design. Look at that, you know? That's 96% efficient, right? What matters is not that all performance ratios good are 90% or better, but that the ones that matter are. And the ones that matter are essentially the highest ones. With me so far? Now we got one more limit we need to check, and that's deflection. We haven't done that yet. Let's just make sure that we're good on that. That should be hopefully a simple check now. So I'm going to give myself a little room for that check there. So what was the limit for this problem? Remember, we got to convert that. So 30 times 12 is 360. 360 divided by 360 is 1 inch, right? And then our actual is, how do we do that again? Simply supported beam, uniformly distributed load.
Squared over 384 times E times IX.
Did you say 5?
5,
And then well, you made 2 mistakes. It's 5 WL to the 4th. What was the distributed load? What was it? 3 kips per foot? And then, what do I need to put up here? There you go. And what is IX for this shape, by the way? What is IX for a W24/76? 2100?
Yes.
It's almost like that table 3-2 has a lot of really good stuff in it, doesn't it? I'm telling you, I'm not kidding. It is one of the most useful tables in the manual. Well, And so what do we get for this? Let's carry it out. All right. The reason why I'm doing 898 is because if I want to do a performance ratio for deflection, I might say 0.898 over 1, which is 0.898. Right? So if we collect all that, we look. So the nice things about performance ratios is see, they're very, very useful to bridge engineers because bridge engineers, they have tons of limit states they need to check. They need to check, different strength limit states, different service limit states. And so if you want to evaluate a design, you can just look at the performance ratios and they tell you everything that you need to know. So I have this problem and I look at this beam and I go, okay, we have a beam that has more than enough shear capacity. Don't even need to think about it. Move on. And then we look at moment and deflection. We see they're pretty close. But which one controlled the design? Which one affected the actual selection of this beam at the end of the day? It was the moment capacity, because that's the one that has the highest performance ratio, right? Whereas if the numbers were reversed, we would probably have picked this beam just straight based on its moment of inertia. We would have had to check the moment capacity, but we would have found it probably didn't govern. It was the deflections that governed. Does that make sense? So those are what are called performance ratios. And sometimes if you hear me use that term performance ratio, it's just sort of a dimensionless, standardized means of looking at performance. And 3 decimal places is like very common. A lot of software packages, that's how they spit it out. Sound good? You sure you don't want a homework assignment this weekend? It's like, we don't want you to have to come up with a solution and an assignment. Yeah. Don't rub it in. Yeah. All right, you all have a wonderful weekend.